welcome back to our afternoon session. I'm very glad to have Daniela Monaldi here from York University, and she's going to tell us about Fritz London and the scale of quantum mechanisms.
It's disappeared. All right, okay. Good afternoon, everybody. Thank you for being here. So I'm going to talk about Fritz London and his seminal idea of quantum mechanisms on a macroscopic scale. This is an idea that London first presented at the International Conference on Fundamental Particles and Low Temperatures in Cambridge, UK, in July 1946. This was the first international meeting of physicists after World War II. As far as I know, the only meeting where particle physics and low temperature physics came together in such a grand scale. So London's aim with this idea was to explain the low temperature phenomena of superfluidity and superconductivity on the basis of the new conception of matter that emerged from quantum mechanics. His unifying interpretation of these two phenomena, which he called superfluids or quantum liquids, was initially quite controversial, but it was eventually vindicated and earned him a place of honor among the spiritual fathers of condensed matter physics. Here we see John Bardeen, who repeatedly acknowledged London's influence on his work. Bardeen credited London for the insight that superconductivity was a quantum phenomenon of a macroscopic scale, and he later explained why the idea had been so groundbreaking. Here we see him, he says, by far the most important step towards the understanding of the phenomena of superconductivity was the recognition by Fritz London that both superconductors and superfluid helium are macroscopic quantum systems. In a more expansive, albeit less accurate vein, Philip Anderson depicted London as a lone thinker who surpassed even Einstein by taking this radical step of assuming the quantum mechanics was right at all scales, including the macroscopic. Now, incidentally, let me note here that physicists today tend to use the expression macroscopic quantum phenomena. This is an expression that London never used, and my guess is that he would have objected to the slippage from mechanisms to phenomena. Nonetheless, I take it as a sign that his explanation of the phenomena in terms of quantum mechanisms has been quite successful. But exactly when and why did London take such a radical step? I found myself quite confused when I tried to answer this question. London himself, in 1950, wrote that the idea emerged quite incidentally in 1934 when he was working on superconductivity in Oxford with his brother Heinz. In a eulogy written shortly after London's death, Lothar Nordheim placed the origin of the idea even earlier. According to Nordheim, the idea came to London naturally when he was working on molecular physics in Berlin before emigrating to London in the 1920s and early 1930s, and then became the leitmotif of all his later work. London's biographer, Kostas Gavroglu, advanced the thesis that the conception of superfluids was the end result, the fulfillment, in fact, of London's lifelong, albeit timid commitment to a specific agenda. According to Gavroglu, London took a very strong anti-reductionist stand even before entering university, and although he expressed his stand only in some early writings, he never abandoned it. Gavroglu claims that London remained an anti-reductionist at heart even after he and Hitler effectively launched the program of reducing chemistry to quantum mechanics. While London continued to work on a quantum mechanical theory of chemical bonding, according to Gavroglu, he started to articulate an agenda based on the non-reductionism of quantum chemistry to physics. And this quiet but persistent, quote, abhorrence of reductionist schemata, end of quote, was finally substantiated years later, according to Gavroglu, in the mid-1930s in London's first elaborations of his remarkable notion of macroscopic quantum phenomena. So there is a certain disparity or disconnection among these reconstructions, and I wanted to know exactly when London came up with this idea, and I couldn't find an answer in the literature. Why do I want an answer to that question? I started examining this because I wanted to find out the role of Bose-Einstein statistics in Gavroglu's thinking, and I hoped as a historian that if I can find out exactly when he first formulated the idea, then I will be able to figure out also how and why he did it. So my analysis, my reconstruction draws substantially from Gavroglu's authoritative biography of London, but I will propose a different interpretation. At least I want to put it out for consideration. I don't claim that I am absolutely right, but I think it's worthwhile to take a look. Namely, I will suggest that the leitmotif of London's work was not really an early intuition of the macroscopic quantum phenomena, but rather a quest to explain phenomena, all phenomena large and small, by means of microscopic mechanisms, with the conviction that the microscopic mechanisms were quantum mechanisms. Now, to be sure, germs of this idea of macroscopic quantum mechanisms can be found retrospectively in his work. When we look at his work in hindsight, his work from the late 20s onward, in his studies of increasingly large aggregates of particles. You may know that London's life was fragmented by forced emigrations, by the politically historical events of the 1930s and 1940s. But despite all the disruptions in his life, his research followed a recognizable path and exhibited a remarkable continuity in the sense that he started from the microphysical scale with the hydrogen molecule and then moved to a larger scale with intermolecular forces and finally looked at macrophysical systems like superconductors and liquid helium. So although there were all these continuities and we can retrospectively find germs of the idea of macroscopic quantum mechanisms, London did not commit to writing any original thought on the scale of quantum mechanisms until the 1940s. On the contrary, what he wrote on the matter reflected rather conventional views. And so we see him in 1946, when he first presented publicly this idea, saying, we have been used to considering quantum mechanics generally to be important only for the atomic and subatomic world, and linked with the world of our perception only indirectly, namely through the medium of averages over thermally disordered assemblies of micromechanisms. Now, my contention is that London's use of the pronoun we in this and similar passages was not just a figure of speech, but London was, in fact, retracing his own intellectual journey as much as that of his colleagues. Reflexive notes of this kind are notably absent from all his pre-war writings, but they became persistent and increasingly assertive in his subsequent work. Now, London belonged to the generation that came of age with the creation of quantum mechanics. His first professional success occurred in 1927 when he achieved in collaboration with Walter Heitler, one of the earliest successes of the quantum mechanics of multi-particle systems, that is the explanation of the homopolar bond in the hydrogen molecule. London's idea of a quantum mechanism mechanism, what a quantum mechanism is, which is the primary ingredient of his notion of quantum mechanisms on a macroscopic scale, derived from this work on the hydrogen molecule. He and Eitler, you are certainly familiar with this, arrived at a quantum mechanical representation of the homopolar bond by following closely Heisenberg's treatment of the helium atom and adapting it to their problem. I will not spend a lot of time explaining this because this is very familiar. London and Eitler found two solutions for the interaction energy, which yielded attraction for intermediate distances. One of them, we yielded an attraction for intermediate distances between the atoms and repulsion for smaller distances, and was therefore suitable for the formation of the molecule. Okay? So now the mathematical form of this solution, of both solutions actually, was very clear. How they arrived at it was mathematically clear, but the physical interpretation was an open question. As they wrote, using classical concepts, the result that the two neutral atoms can interact in two different ways can only be described very artificially, and they say quite clearly, we are probably still far from a real understanding of this issue. They added more far-reaching considerations quite timidly in a footnote. They wrote that the twofold degeneracy of the energy with which they started and that gave the final solution of the problem had no classical analog, so this was really a quantum mechanism. They used the statistical interpretation of the wave functions, and they read their wave functions as meaning that, unlike the classical case, in the quantum case, for any value of the potential, there always existed a probability of exchange, Austausch in German, of the two electrons in the molecule. As Eitler would recall later in his interview in 1963 with John Heilbronn, it was not clear what exactly was exchanged. At the beginning, they believed that it was necessary to explain this exchange in familiar terms, but they eventually became convinced that, and I quote, it had to be taken as a fundamentally new phenomenon that has no proper analogy in older physics. Really purely quantum mechanism. And then they connected this probability of exchange to the quantum statistics that Bose and Einstein and Fermi and Dirac had recently published. So they say in this footnote, while in classical mechanics it is possible to label the electrons, nothing like that is possible in quantum mechanics. Because the two electrons can always be exchanged with one another. And because of this, a type of statistics which in principle forgoes an individuation of the electrons and only considers their number distribution in states, such as the Bose or Fermi statistics, is very appropriate to the quantum mechanical possibilities of description. And I point out this footnote because a consideration of this kind and a link between the impossibility of individuating the electrons in quantum mechanics and the way of counting states in the quantum statistics comes up here, but it will only resurface again in London's writings 20 years later when he starts talking about macroscopic quantum phenomena, which is in itself, I think, something interesting. In all his work on quantum chemistry, on the theory of valence and on intermolecular forces, London insisted that you did need these quantum mechanisms to explain and provide a quantitative account of the forces that arose among atoms and among molecules. But once you had this quantitative account of the forces, in fact, you could represent the forces semi-classically as additive forces between point masses that corresponded to a rather classical representation of the van der Waals forces. Okay. Actually, the first quotation that I've reported here is from a review article by London of 1929, where London, in fact, claims that now that this mechanism of how the interactions come about has been understood, then it will be possible to explain the rules of chemistry by means of quantum mechanics. We are all familiar with famous pronouncements, by, for example, by Dirac about, now the possibility of reducing chemistry to physics was open. It seems to me that this passage by London is just as strong a statement of that strategy of theory construction as the ones that are more famous. Again, I mean, there was this possibility of reducing chemistry, the chemical rules, to quantum mechanics, but at the same time, as I said, the quantum mechanisms, it's pretty clear from this work of London, the quantum mechanisms acted at the microphysical level and did not manifest themselves directly at the macrophysical scale. This can be seen in his work in this area up to the second half of the 1930s. Now, on the basis of this evidence, of course, one cannot exclude that the study of intermolecular forces had already given London the intuition, the quantum mechanisms could act directly on a macroscopic scale. Maybe he had already privately begun to speculate about how large molecules would know what was happening at the far end, which is what Nordheim recollected 18 years later. Nonetheless, it seems more likely from the evidence of his published work that what London had acquired up to that point was a firm grasp of the notion of what a quantum mechanism is and of the fundamental importance of quantum mechanisms to explain the appearance of intermolecular forces, and that he was working towards the elucidation of these effects of these non-classical features at progressively large scales. But the idea of macroscopic quantum mechanisms is still not there. Now, in 1935, together with his brother Heinz, with whom Fritz had reunited in Oxford, he turned to the field of low temperatures, and his first result in this new field was that of providing a macroscopic description of superconductivity on the basis of the magnetic effect that had been recently discovered by Walter Meissner and Robert Ochsenfeld. Now, the London equations, this theory of, or theoretical description of superconductivity, is one of the most famous examples of a theory that today is described as being a phenomenological theory, not only today, but also back then. I just want to talk about this to clear some equivocation on the meaning of this term. Of course, phenomenological did not have anything to do with the philosophy of phenomenology that Fritz London had been a sympathizer of and was a sympathizer of. He famously wrote a thesis in philosophy to obtain his doctorate from the University of Munich that had been published in the Journal for Phenomenological Research that was edited by Edmund Husserl. But Fritz was, of course, completely familiar with the fact that physicists did not use used the term phenomenological to refer to that philosophical tradition. They used it in the same sense as this time, they used it in the same sense as they use it today, to talk about a theory that only uses macroscopic measurable quantities, describes relations among those quantities without referring them to microscopic mechanisms. So when London knew that his equations had been described as macroscopic, and he did not like that. He did not like that characterization. In his speech for the awarding of the Lawrence Medal in 1953, he remarked that although the London equations had been often called phenomenological, they actually went beyond what is directly given by phenomena. He pointed out, he had already pointed out together with Heinz that their equations were only a macroscopic interpretation, but he also made clear that the value of this interpretation is that it provided a basis, a starting point towards constructing a microphysical explanation of the phenomenon. Okay, okay, so since I don't have much time, I want to go quickly over another work for which Fritz London is quite renowned, which is a work that he co-authored with the French physical chemist Edmond Bauer at the end of his stay in Paris. After Oxford, he moved to the Institut Henri Poincaré in Paris, where he continued to work on low temperature physics, and in fact he turned to superfluidity, but he also produced a work on the theory of observation in quantum mechanics, and this is according to the preface, this is the expanded version of a series of lectures that he gave at the Sorbonne, but I have not been able to actually date this work exactly, and I will explain why I would like to do so. I would like to be able to know exactly when he gave those lectures, because it seems to have happened at the same time when he was getting at his most important breakthrough towards the formulation of the concept of macroscopic quantum phenomena. However, in this work, which is a work that's specifically dedicated to the interpretation of quantum mechanics, he gives no sign of that idea, and in fact the work is actually quite explicitly and clearly based on the conventional idea that there is a stark demarcation, a stark distinction between the quantum objects of observation, which are atomic and subatomic phenomena, and macroscopic phenomena. And actually, London and Bauer go on to explain that this distinction implies almost two different levels of two different concepts of reality. That in the case of macroscopic phenomena, one is still justified to use what he calls a naive realism, or a naive idea of reality that is based on the possibility of attributing properties to particles in a continuous way, while at the microscopic level, at the level of quantum mechanisms, that idea has to be replaced with a more abstract idea of reality and objectivity. Okay, so it seems to me that this again is a pretty clear pointer to the fact that he still had not arrived to the idea of macroscopic quantum phenomena. The work that gave him, his finally ingredients to work towards that idea was his interpretation of the Lambda transition in liquid helium, which is a work that he published in two parts in 1938, at the beginning, the first initial publication at the beginning of 1938, and then the second more extensive analysis in October. And this is a theory where he suggests that, in fact, this lambda transition in liquid helium can be understood as a case of Bose-Einstein condensation, and this is where he begins to make the link with the quantum statistics again. And he really constructs an understanding of Bose-Einstein condensation that will allow him to claim that this is a macroscopic quantum phenomenon. But what is interesting here is the difference between his very first publication, where he proposes this idea, and his second publication, where he becomes much more cautious, much more self-critical, and he ends up actually admitting that while he has advanced the theory of Bose-Einstein condensation, the application, the possibility to apply this theory to superfluid helium or superconductors is only hypothetical. He was more than aware of all the gaps and limitations that were implied by this analogy. Now, again, sorry I have to rush about all of this, but I will be happy to answer questions. The first appearance in writing of something that sounds like the idea of macroscopic quantum phenomena comes in a private letter that London wrote when he had, again, emigrated from Europe to the United States during the war in 1941. He was at Duke University, and he was writing to a biochemist, William Perlsweig, to comment on a work by a physiologist who had proposed the possibility of an application of quantum mechanics to biomolecules, to the macromolecules of biochemistry. And in this case, London comments that macromolecules may have a kind of amplifier construction which may produce an enlargement of the quantum effects instead of their usual annihilation by averaging. Okay, and in these cases, then the rule of quantum mechanics might be felt even in macroscopic dimensions. And London says that he had been investigating that possibility from a more physical point of view. So it seems that at this point he had started thinking about macroscopic quantum phenomena, the possibility of quantum mechanisms manifesting themselves in large dimensions. What actually triggered the formulation of that idea that he then will make public and present in full in 1946 is the occurrence, the eruption of a controversy between Tisza, who had produced a theory based on London's idea of superfluidity as being a case of Bose-Einstein condensation, and Lev Landau, who disliked and actually was quite derogatory with respect to that idea. It seems that in the context of this controversy, London felt that it was the case to, first of all, reconsider Tisza's theory, which he himself had been quite dismissive of at the beginning, and to go back to reconsider his own analogy between Bose-Einstein condensation, superconductors, and superfluidity, and that is when he becomes an ally of Tisza on this controversy, and then at the conference immediately after the war, he will present the idea of macroscopic quantum phenomena. So, and he also, not immediately in 1946, but a few years later, returns to the concept of the loss of individuality of particles that is implied by a phenomenon such as, or an effect such as Bose-Einstein condensation and by quantum statistics in general, connecting the loss of the possibility of individuation of particles in quantum mechanics with the counting of states in quantum statistics. So let me come to my concluding consideration. I just want to point out that the claim that has been made that London started thinking about macroscopic quantum mechanisms in the 1930s or even earlier would leave us with a mystery. How come that he never wrote a single word on this until 1946? So that's why I would like to suggest and propose the possibility that, in fact, we have evidence that London did not arrive at that idea until at least the 1940s, 1940, 1941, possibly even later, that he acquired all the necessary ingredients for that idea during the course of his work, but he only put them together to produce something new. At that time. And this follows a common pattern of slow, I should say, sputtering realization of the full significance of the loss of individuality implied by quantum statistics. Thank you.
The timing was impressive. Exactly half an hour. Okay, so we have time for questions. Yeah, Christian. Christian, you start.
One comment and a question. Sorry for that. Thanks for the great talk. That was really exciting. One question is, in like the old quantum theory, or I should probably rather say before quantum mechanics, there is the concept of like macroscopic electron orbits in, for instance, Einstein's 1922 paper on superconductivity, where he has these conduction chains, which goes back to Fritz Haber and other people's ideas, and is actually developed further even after quantum mechanics by Percy Bridgman. And there they simply assume a Bohr model for the atom and assume that like a big molecule is formed simply by touching Bohr orbits. And because there's no dissipation in a Bohr orbit, you can basically have like very extended electron orbits that explain superconductivity as dissipation as transport, as skipping orbits along these atoms. Yeah. So do you see any connection to London's conception?
No, and in fact it's rather puzzling. Considering, London's, of course, exposure to the field of low temperatures, he seems to be totally unfamiliar with this previous work on superconductivity by Einstein and others, in the same way as he seems not to be aware that Einstein had returned to an attempt to explain superconductivity when he published the Bose-Einstein gas papers. When London mentions quantum theory in his review papers, and he sort of gives his historical narrative of the development of quantum theory, he only refers to the theory on the structure of atoms. So he is totally, up to, quite late, is totally within the perspective of the Bohr-Sommerfeld tradition of explaining atomic structure. So quantum theory for him is a theory of atomic structure. He seems to have lost track or memory of the complex interactions of chemical physical chemistry, thermodynamics, and statistical mechanics that have given rise to quantum theory. And he seems to be rediscovering this late.
So actually, that was my comment. Sorry, I know. So the question is very quick. Like in 35, he speaks of like a single large, big, like diamagnetic atom of treating them. Why isn't that a macroscopic quantum state?
Yeah, it's a good question.
Or
I think that is in fact one thing that I will go back and inquire better, because if you remember, when he, in 1950, when he says, when he first had the idea of macroscopic quantum phenomena, that's what he says. He had the idea when he was working on superconductivity. Okay, now he says in 1934 with Heinz. In his work with Heinz, I don't see any inkling of the idea of macroscopic quantum phenomena. They only do the phenomenological relations. But then London goes back to look for the microscopic explanation of those relations. And in fact, he published a thesis from the University of Paris. He gets a doctorate in Paris because he needs that to achieve a position at the Institut Poincaré, where he works on a new conception of superconductivity. And that new conception is based on an analogy with between a superconductor and a diatomic atom. And he explains that a diatomic atom cannot be treated with localized wave packets, that you have to use a single large wave function. So it is quite possible that, again, this is one of the key ingredients that will lead him towards the idea of macroscopic quantum phenomena. But then again, that ingredient by itself is not the idea.
Oliver?
Daniela, first, thank you very much for the wonderful talk. I have a comment, but it depends on if I really understood one point. So I have a question and then a comment. When you presented the London and Boer this small booklet about the theory of observation, did you say that London accepted or criticized the stark distinction between quantum system and macroscopic phenomena? Can you come back?
They definitely accept that. They take it for granted. When you're talking about his theory of measurement.
I have a different interpretation of this booklet, this text. I think that which is strong in this text is that while following von Neumann's treatment of observation, they accepted what von Neumann had suggested to treat a quantum system and the measurement device as a quantum system.
Yes.
So I don't think that he is accepting this stark distinction. That's why I think that he was criticizing this stark distinction. That's why he needed to introduce the role of mind or consciousness of the observer, something which von Neumann did not make, but it's a logical step when you accept the validity of quantum mechanics for this joint system, quantum system plus measurement devices.
Right, that's correct. And yes, of course, this monograph by London and Bauer, presents itself, they present it as being a clear and concise exposition of the statistical interpretation of quantum mechanics, which they take has already been established. In fact, in 1927, they say, and of von Neumann treatment of the problem of measurement, which they say is an in-depth discussion of the problem, but it is very formal and not so accessible. So they want to give a simple and clear explanation of what von Neumann has done. Okay, that's what they declare. They don't want to criticize von Neumann. They don't want to propose anything new. In fact, arguably, they actually go beyond what von Neumann has done, because they are the ones who suggest that there is an essential role for the consciousness of the observer in the act of observation, which was not there in von Neumann. But besides that, they don't depart from von Neumann in saying that the act of measurement has to consider the coupled system of the observer, the apparatus, and the object of observation. But the act of observation implies that you have to decide what your object of observation is. Okay, and that's where they make the distinction. The object of observation is quantum. And they say quantal, actually, that's the adjective that they use. The process that corresponds to the act of measurement is macroscopic and not essentially quantal. They say that quite explicitly.
That's exactly where we disagree.
Okay.
It's a matter of interpretation of this. But
I'm ready to be illuminated.
Yeah, but this disagreement has some implications. My implication is that he needed the role of mind exactly because for him a macroscopic system should be treated through quantum mechanics.
Okay.
In 1939. That okay.
Yes, of course.
Sorry. I think, don't forget that London is a phenomenal, is deeply influenced by phenomenology, right? So at this point, right, I think what von Neumann says is actually that you have these two equivalent descriptions, right? You have a macroscopic, you know, in his chain of descriptions, right, that there is the possibility of giving a description as a big superposition and as a reduced state. Whereas I think what London and Bauer say at this point is that we know which is the correct description. It's the macroscopic description, right? I mean, that's the role of consciousness, right? To show us that at this point the formalism is just not right anymore. So I think I'm with Daniela on this, that it's not a matter of sort of, you know, some additional mechanism that breaks down the correct, that sort of changes the otherwise correct mechanism of macroscopic quantum mechanics, but it's the fact that at this point the quantum mechanical description fails because it just, you know, there's something more fundamental that we know about nature at this point. Alexei was...
Yeah, there is something that puzzled me before with regard to this story even. I don't understand why people like Bardeen and Anderson would say that idea of macroscopic quantum state was controversial.
No, sorry. If I said that, I did not mean.
Why they say this, because
No.
I mean there are tons of things where quantum phenomena are displayed. Like say, laser is a macroscopic quantum phenomenon, or state is kind of aware. I don't know if anyone would object to Bose-Einstein condensation
Being called a macroscopic quantum phenomenon.
No, yeah, I mean, so
Yeah.
it's,
No.
it's so relatively. I mean, Einstein didn't call it macroscopic quantum thing, but he did introduce it in 1924, and as far as I know, nobody objected to it. To the something. So
Yeah.
why do they?
I'm
why
afraid
do they do this thing? I don't understand. That's what.
because it seems to me, my answer to that, and I may be completely wrong, is that they are using the rhetorical tool of referring to a unified Copenhagen interpretation to which they want to object, and they attribute the idea that quantum mechanics applies only at the microscopic scale to this conventional mainstream interpretation of quantum mechanics.
Or another possibility would be that Lambda object to a very specific way how Lambda displays superconductivity, but not to the idea of
Yeah.
So there was a lot of controversy about Lambda's specific theories.
Yes, correct. Yeah, that is what I meant when I said the London's interpretation of superfluids was controversial. I did not mean that the idea of macroscopic quantum phenomena was controversial. I presented these two quotations to just show how, certain solid-state physicists made London their patron saint because he had invented the idea of macroscopic quantum phenomena. Okay. So, I mean, if you read Anderson's writing about London, it's very hagiographical and it's fanciful. I mean, he makes up a character that did not exist historically.
May I ask a minor technical question? This idea with the macromolecules being somehow, amplifying quantum mechanics to a larger scale, that I didn't quite understand.
Neither do I, and I have to confess I did not have time to look into that. I mean, the early 1940s were the time where physicists were starting to look at macromolecules for various reasons. That Schrödinger published What is Life in 1944, but also, there is a big interest in the physics of polymers. In the United States, there is a big government-funded program on rubber materials after the beginning of the war, when the Asian market of natural rubber had been closed, and several quantum physicists who had immigrated to the States got enlisted into that program. This is really a time when many physicists start to take an interest in macromolecules.
It's just that this notion of amplifiers...
No, yeah, that I cannot answer technically your question, because I don't know what it was meant by that. I did not have time to look at what kind of theory or proposal London was reacting to when he wrote that letter. It was apparently something that the physiologist Albert Szent-Györgyi had written about explaining macromolecules by means of quantum mechanics, but I still have to look into that. I don't know.
Question, Michel?
So since Bauer came up, so the first day of the conference, we actually heard that Bauer was one of the first people, like in France, to look into quantum stuff, like really early in the 1910s. Do you know anything about like his career? Because I only know him because of
Very
this one paper
little.
with-
I've been able to find out very little about him. Apparently, he was Paul Langevin's vice director.
Correct.
And he was a renowned physical chemist, and he had been London's translator for a series of lectures that London had delivered in Paris when I believe he was in Oxford looking for a job in Paris on superconductivity. It's not completely clear, it's not clear at all, in fact, what role he had in co-authoring the monograph, you know, if he was really a co-author or he was just collaborating with London for putting out the monograph in terms of, you know, writing in French and things like that. That is something that I found no information about.
Okay, thank you.
More questions? Okay, then let's thank Daniela again.